So here I was thinking that Dan's not going to badmouth my second talk, but if anyone's going to talk behind my back tomorrow, just remember Mike Lemon gave at least one more talk than I did at this conference. Okay, all right. I really wish I'd given this talk prior to the other one. This was supposed to be my student's talk, but he didn't make it here, and so I'm stuck giving it. More than happy to. So everyone's already seen this event, except those who came in late. We're talking about the 8th to 9th March 2008 geomagnetic storm. Again, to quickly remind you, in the 10 minutes that I have, there are 2 CIRs in this event. This is the first one. This is the second, and it's really right at the second CIR where the magnetic storm starts. You've seen this plot before as well, and here, just to point out, is the... Do we have the... is it up there? I think somebody took it with them as a souvenir. No, here it is. Okay, thank you. All right. So SIMH goes positive. Here's a negative incursion due to a substorm, and second negative incursion due to a substorm. This, the high-speed stream starts around here somewhere, and the second CIR then sets things going. So 1, 2, okay. Now I'm going to show you a movie of the MHD simulation. I'm going to look in the same equatorial plane I was talking about. You can see a very big discontinuity. The bigger the IMF BY, the bigger this discontinuity is. But basically, if we look at the tail region, we're looking at the equatorial plane in the magnetotail. Here's BZ and VX, and the spacecraft trajectories of Themis B and C are shown as we go along. So let me start this, and hopefully it'll start. There we go. All right. Time is flying by, but if you look at the magnetotail, you see that it's churning already even before the first CIR hits, and after that you're getting all sorts of flow channels undulating back and forth. Here you can see the velocity, a lot of stuff happening in the MHD simulation. We're in the middle of the CIR now. The windsock, BYBZ, it's like a hurricane is going by. You can see just what's going on in the tail. So this notion, as I said in my previous talk, of ions, well-behaved ions, going into the tail and convecting earthward on some time scale is simply not going to happen during this event. That's the second substorm that goes off right there. We're in the high-speed stream now, and things are going to quiet down a little bit, comparatively speaking, until the second CIR hits, and then again all hell is going to break loose. And at the same time, we're going to have all sorts of alpha-anic turbulence in the solar wind that's going to drive everything from boundary perturbation, some of which you see here, to very high-intensity activity in the tail. And you can see that. And you can see that by the end of this event, the 2 Themis spacecraft are getting extremely close to each other. So we've simulated this all the way to about 8 o'clock UT on the 9th of March. And it's going to stop just in a minute. There we go. So in order to validate our MHD model, we took the Themis B and C spacecraft locations, and this is the Themis B orbit, Themis C is over here, and the red portion corresponds to actually a lot more than that. It's the entire event that we have simulated. And if I put the Themis B result, Themis C is very similar to this. We see that we have really, really good agreement. This is the entire simulation. It's 28 hours of the simulation. The only time we're off by a bit, and we're doing well on the BZ but not on the BX and BY, is right after the high-speed stream for about a period of 2 or 3 hours. But aside from that, we're doing a really good job of reproducing what the spacecraft flying through a very turbulent tail is doing. Now, for the rest of the talk, I want to concentrate on some really interesting features we see. If you look at the interval right after the high-speed stream at 1830 UT onwards, this is the density in the MHD simulation, again the equatorial plane, on the dawn flank. So this is the noon-midnight meridian. Here's dawn. And you see this feature that develops at about 20 RE down the tail and travels tailward and then dissipates. And this is happening at a time where the IMF-BZ goes through at least 3 turns very, very quickly. And if you follow those streamlines, if you draw a line along the contour corresponding to 2.5 particles per cc density in the MHD simulation, and you stack it as a function of time, the y-coordinate means nothing. We just stack it so we can see it. Color coding is according to the time. So over the period of, say, 7 minutes, this thing unravels and it goes tailward. And if we just put lines around where we think the leading edge is, it goes from about 20 RE to 26 RE, and that's a speed of about 75 kilometers per second. Now, if we trace field lines into that region, then I'm going to step through. This is about 5 minutes before it develops. It's kind of hard to see that this is exactly that same region, but we're looking from the tail towards the Earth. This is the dawn flank, dusk flank, so we're down the tail looking in. Blue field lines are closed field lines. Yellow are open, and you can see that there's a lot of structure in the mid-tail region. They're closed field lines, but they're not well-behaved closed field lines that we'd like to see. And we see some stretched field lines in the flanks and these open field lines stretching down the tail. Now, if I start stepping through, here's some very interesting things happening closer to the mid-tail region. Just as that structure starts developing, we start seeing these draped field lines that have just opened up, and that's how plasma is streaming in to the magnetosphere through these field lines. So that kink that you saw, as insignificant as it may seem, that actually is supplying plasma to the magnetosphere at this time. And then 2, 3, 4 minutes later, and it's gone. That's the rest. Now, this is one of my favorite periods during this storm because this is a snapshot of the BZ at 2 different times. And you can count somewhere close to 10 reversals of BZ just in this panel. So that's how turbulent the solar wind is during this time. The average doesn't do it any justice, but you can see it going from 40, 45 RE down the tail to 15 RE upstream. There's a lot of changes going on. And again, if we take the contour that corresponds to 2.5 particles per cc and stack it as a function of time, this is the kind of thing we see. So we're not really seeing KH instabilities on the flanks. Things are just changing too fast for anything stable to be going on. But you can see that here's that same contour starting from 6:30 and going to 6:56 on the 9th of March. And we start out having a pretty smooth contour, and then this vortex kind of a thing develops, and then it unravels because by this time the IMF has changed signs 7 or 8 times. Now, one of the more recent things that we did was we looked at the energy density in the MHD ring current on the night side again as a function of dynamic pressure and VXBZ in the solar wind. So the positive VBZ corresponds to southward IMF, negative VBZ corresponds to northward IMF, and the gray regions are the negative southward IMF regions during this. And so we've separated this into 2. What's going on here? Why do I have a finder icon in the middle of, oh, geez. Okay, one more time. There we go. Oh, there we go. So we've separated this into 2 portions, 0400 UT to 1830 UT, right before the high-speed stream. And the second portion, there we go. Second portion is going to be afterwards at about 1900 UT up until the end of our simulation. And the data I'm going to show you, I've tried to correlate the ring current energy density to what's happening in the solar wind. We've thrown away any data where the solar wind, where the IMF changed sign, IMF-BZ changed sign less than 30 minutes prior. And what I've done is I'm going to be showing you the ring current energy density as a function of dynamic pressure for those 2 periods. This is all of the southward IMF periods in that initial CIR, and you can see that they're grouped at very high, relatively high energy density, but there's really no correlation to them. Northward IMF for that period, and you see a real good correlation. I mean, R is, I think that's R squared, 0.877. almost linear increase in dynamic pressure, in ring current energy density with dynamic pressure, even though it's a factor of 2 at least less than what we had for southward IMF. Going into the second CIR and high-speed stream, again, southward IMF, a lot more scatter, again, 20 and above. And northward IMF, any northward IMF that's happening during the high-speed stream is in the middle in that quiet time, and we're getting very little ring current energy density, and they're all clustered together. So if we put all of this together, of all of these, the only one that really shows any correlation is northward IMF during the first CIR, and you see that linear relationship there. And that's all I have for you today. So basically, what I wanted to demonstrate was how variable the magnetosphere was during that time and how miraculous it was to actually get ions from the ionosphere and the solar wind into the inner magnetosphere like we did in my previous talk. We saw the boundary perturbations, and in fact, we're going to be publishing a paper on entry through those regions because we've shown those to be entry paths for ions. And finally, you saw how the response of the night side ring current in the MHD was linear for northward IMF during the first CIR, but then completely scattered for all the other periods. That's it. There you go.
Vahe, I was just wondering about the desirability of including ionospheric H plus in your model.
There is definitely a desire, but what I would like to have is a model that's responsive to changes in the IMF and things that are happening in the tail on real-time scales. From what I've seen, the models I've found, maybe I'm not looking hard enough, are basically step functions, low activity, high activity. Once, if I can find a model or talk to someone who has a model that does H plus outflow from the ionosphere on responding to everything that's happening in the magnetosphere, then absolutely, yeah, I'd like to do that.
Yeah, I think that's what Bob is doing. So good, maybe there's an opportunity here.